the first thing we're going to talk about is the structure of these aromatic components. And you can see that here, in this case, we are having 6 carbon atoms that are connected in this circular fashion. All these carbon atoms are again sp2 hybridized, and what this means is that we have these 3 sp2 hybridized orbitals at each carbon atom, and perpendicular to that we have a lonely p orbital that is basically sticking out from this plane. And as you can see here, we are having 2 sp2 hybrid orbitals forming carbon-carbon bonds, 2 adjacent carbons, and the last one forms a carbon-hydrogen bond. And with that, we also find this binding angle of 120 degrees that we've also previously discussed when we talked a little bit more general about the sp2 hybrid orbitals. And after we have established the body of, or the framework of this carbon hydrogen component, we still are left with 6 p orbitals that are each filled with 1 electron in this case. And these electrons, or these p orbitals, also overlap as they did with the double bond, but now basically you can assume that always 2 of these p orbitals are now overlapping and forming a pi bond. And with that you can conclude, okay, 6 p orbitals means 3 pi bonds that are formed, and this is represented here in this drawing here. But of course the overlap towards the one side is as good as the overlap is to the other side, so basically all these p orbitals form like one cloud of pi electron density above and below the ring structure formed by the atom cores. And that is represented here in this delocalized structure, where basically we are drawing a circle representing these 6 pi electrons to show that basically all these bonds or these electrons are located at every carbon at the same time. And in this picture here, you can again see that the p structure, or the pi bond structure, is now delocalized, as you say, above and below the ring plane, and this electron density can then be used to perform certain reactions.